All right. Hey, good morning, ladies and gentlemen in chemistry. So today's plan is essentially to cover the quiz. Let's talk about some things that I saw, and let's go through each answer and really dive into it and explain it in case you were stuck or confused. Now, if you have not taken this quiz, I extended the deadline to Monday night, tonight at midnight. So go ahead and take that before you watch this video, right? Don't cheat yourself out of figuring out how well you're going to do on this test coming up in 2 weeks. You're going to serve no purpose by just watching this video and filling in the answers blank, all right? This isn't the point of this, right? It's not graded. I want you guys to practice and feel prepared when it comes to the test. So, our first question is, right, the energy required for an electron to move from one energy level to another is called, right? What is that called? And that's something we covered in our digital notebook, right? What is a quantum? It's the amount of energy needed to make or to move an electron up one level in energy, right? To move an electron from ring number 1, that first energy level, up to ring number 2. That is a quantum, that how much energy we need to put in. That's called a quantum. 2, how many electrons can each orbital hold? How many electrons can each orbital hold? So when we talk about this, I wonder if I can pull up the answers. Here we go. So remember, our orbitals are the bunk beds, right? Our orbitals are those little boxes, and we have never put more than 2 electrons in each box or in each bunk bed. They're only ever going to be 2, and they're only ever going to be facing different directions, right? One arrow pointing up and one arrow pointing down. Cool. So that would be 2. There's only ever 2. Whenever we do an orbital diagram, in an orbital, we only ever put 2 electrons. On the third energy level, or floor, right, that third ring, how many sublevels or rooms are there, right? And this, I figured this question would get a little confusing for you guys, and it looks like it might have stumped some people, but think about it this way. You guys can use your notes on the test. If you look at this table in your notes, you can go ahead and look at principal energy level. That's our floor. Right? This is our floor. So what floor are we on? Well, it wants to know about floor 3. And it wants to know how many rooms are in floor 3. Well, we have an S room, we have a P room, we have a D room, and that's it. Right? So on the third ring, or that third energy level, we have 3 different rooms we could put electrons in. So your answer for number 3 should be 3. 4. How many electrons exist for oxygen, right? If we're talking about a non-ion, right? Something that isn't charged. This is a neutral oxygen atom. Well, we just have to figure out how many electrons there are, and we're going to use our periodic table to figure that out. We can go ahead and find our friend oxygen, which is right here. If we were in class, I would say, what does that number 8 mean, right? Well, that number 8 is its atomic number. That means it has 8 protons. Oxygen always will and always has had 8 protons. That will never change. But when we're talking about electrons, right, and it's neutral, we need that to balance out. Our protons must equal our electrons to make a neutral atom. So we're going to go ahead and know that there are 8 electrons. There are 8 electrons in a neutral oxygen atom. No charge. Order the following parts of an electron configuration in order for phosphorus. E. Okay, so let's just make it easier on ourselves instead of going into the answer. Let's just write out the electron configuration for phosphorus. So what I recommend is going to the periodic table and finding your target. So we want to be at phosphorus, right? We want to be right here. Now what we need to do is essentially work our way to here by reading left to right on the periodic table. So let's do it. Okay, so we have first, we're at our first floor, right? 1s. We have 1s2. We have 2s2. We have 2p6. Right, because we're still not at phosphorus. Then we have 3s2. Then we have 3p, and then we're at our target 3p3. So our total electron configuration, looking back here, we would be, oh, I don't like that one. we would be at 1s2, 2s2, 2p6, 3s2, 3p6. All right? So just remember, we read the periodic table left to right. And if you want help with that, actually come check out your digital notebook. And you will see this will help you out a lot. This table right here, right? We have our 1s's, we have our 2s, 2p, 3s, 3p, 4s, 3d, 4p. This gives you the exact order if you read it left to right. So I start here, then I move left to right, and that gives you your exact order. Which of the following represents an electron in the excited state? All right, let's go check it out. So remember, our excited state, that just means something where an electron gets bumped up in energy level where it's not really supposed to be. So we have to look for one that has an electron out. So this looks normal. 1s2, 2s2, 2p6, 3s2, right? That looks fine. This one, 1s2, 2s2, 2p6, there's nothing different about that, 1s2. But this one here, we have 1s2, 2s2, 2p5. We didn't fill that fifth or that last spot on the 2p sublevel, right? That electron got bumped up to 3s1. So this one, because we didn't fill this up with all 6 electrons that it can normally handle, we see that one electron got bumped up to that 3s level, which means it's in the excited state. All right, our next question is, when filling atomic orbitals, what orbital do you fill first? I feel like I shouldn't even have to cover this one. You guys should be pros at this. But, of course, remember, we always start in the top left of the periodic table, which is going to be our 1s. Even if we look here, we see 1s is always going to be where we start at the very top. Now, this one. What is the correct orbital diagram for boron? We have 4 choices here. First thing we have to do is figure out how many electrons boron has. And in our periodic table, we see boron is element number 5, which means it has 5 protons. Boron has always and always will have 5 protons. And in order for it to be a neutral, it has to have 5 electrons to balance out. So, first thing we need to do is find out which ones have 5 electrons. We have 1, 2, 3, 4, 5. That one's good. We have 1, 2, 3, 4, 5. That one's good. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so all of them have 5 electrons. So that means they're all the right amount of electrons. Now we have to start filling it up in our own head as if we were writing it out. So we know we always start with 1s1, right? 1s1 and 1s2. We always fill that one up. Well, if we look at number A, they didn't fill up the 1s suborbital before they filled up all these other ones, right? So this one, it didn't say anything about being excited or anything. It's just the normal electron configuration. So that is out of here, right? We always fill up our rooms before we move up to the next floor. These other 3, 1s, it looks like it's good, right? They all have 1s filled up. Now next we would move to 2s, where we'd fill that one up too. And all of a sudden, we start to see, well, this one has it completely empty and 3 over here, right? It's not excited or anything. It's just, this is just wrong. That's gross. Get it out. And this one, right, what they did is they split up the electrons before they filled that S room. Remember, we always want to fill the previous room before we move up to the next room. And then we can start spreading them out. But we need to fill this up first. So this one's wrong. But this one, this is totally good. B is right. Because we fill up our 1s room, we fill up our 2s room, and then we move on to our 2p room. Next, we have, which element is this an orbital diagram for? Now there's a really easy way to do this. All we have to do is just count the electrons. We have 1, 2, 3, 4, 5, 6. We have 7 electrons. Well, it doesn't say anything about it being an ion. It says it's a neutral element. Which element is this for? Well, we know we have 7 electrons. Let's flip on over to our periodic table and find out what should have 7 electrons when it's neutral. And after a little bit of looking, you see, oh, nitrogen has 7 protons. It always has and it always will have 7 protons. So in order to be neutral, it's going to need 7 electrons. So this is an orbital diagram for nitrogen. What sublevel comes after 4s? Now, a really easy way to figure this out is just look over here. Look at our notes that we took. On the fourth energy level, we have 4s. What comes right after 4s if we're reading to the right? Well, 3d, of course, right? We see 3d comes up next when we're writing out our electron configurations. What is the proper electron configuration for vanadium? Well, let's go ahead and look for vanadium. And we see vanadium is right here in our transition metals, right here in the middle. So if we were to do this in our head, we would say, okay, 1s2, we have 2s2, 1, 2, 3, 4, 5, 6, 2p6, 3s2, 3p6. Now we're at 4s2, and then we go not to 4d, we go to 3d, right? 3d, 1, 2, 3. So we should have, we go all the way up to 3d, 3. Slip back over, clear. We should have for vanadium, we should have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d3. That's our electron configuration for vanadium. What is the proper noble gas configuration for gallium? Remember, our noble gas configuration is like shorthand. So, if we flip back here and we look for gallium, we see gallium is right here. We have to look at the most previous noble gas. Remember, noble gas is being this whole right-hand row or column. We have to look at the most recent one we encountered, the most recent noble gas that we had passed, right? And that's going to be argon, right? Argon. So we would start, when we're writing this out, I'll write it out up here, right? We would start with argon in parentheses, its atomic symbol in parentheses. And then we go to, well, this is 4s2, 3d10, and then 4p1. So flipping back over, because we just continue on as normal. We would see that for gallium, we would have in parentheses Ar, then we'd have 4s2, 3d10, and then I think it was 4p1. There we go. That's all you got to do. Match each energy level with how many electrons it holds. I'm not going to cover this one in depth because you can look here. Each energy level. How many electrons does each energy level hold? Well, S's, they hold 2 electrons. P's, they hold 6, right? Just whatever our table says over here. Whatever our table says over here. All right? All right. Kamala is tasked with creating the orbital diagram for phosphorus. Below is her work. Create an audio-video response. Kamala did incorrectly. So first thing we need to do is look up phosphorus, and we see phosphorus has 15 electrons. Let's make sure she did that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. She did great. She knew that. But the issue that we see with this is that in this 3p level, right, she paired up these 2 electrons before spacing them out. So in reality, we should get rid of this down-facing electron and put an up-facing one in this room, because they like to be spread out unless they have to double up. They like to be spread out unless they have to double up. Very good. And I think we just have one more. We have a minute to cover it. So lithium provides a bright red color when introduced to a flame, right? We saw this. Given this information and diagrams below, identify which energy transition most closely relates to the color. So it's asking how high of energy is this transfer? So we see bright red color, and we see this is the color that's sent out, right? That bright red. And we know red is the lowest energy. So we have to ask ourselves, how do we get the lowest energy to come out of this reaction? Well, I'm going to ask you guys a question. Do you think an electron falling from up here down to here is low energy? Or do you think an electron falling from here down to here is low energy? Right? I'll leave that one up to you guys. I think my recording is done. Yeah, I got 15 seconds left. So, think about it. Which one's going to have the higher energy? The one falling along a far amount, or the one that doesn't fall very far at all? Very cool. See you guys.